All right, what we're going to be talking about now is called the band of stability. Now, I know that in labs, when you produce your graphs in labs, you're expected to write titles that reflect the behavior or how the independent variable affects the dependent variable. In fact, your title should say the effect of, and then you tell me what the independent variable is, and then on the, and tell me what the dependent variable is, okay? But this is actually not quite the same thing. It's just showing the relationship mathematically, just numerically really, between the number of protons and the number of neutrons in all the stable isotopes, okay? All the stable isotopes. So what we're looking at is a comparison of protons and neutrons in all the stable isotopes. So, if we're going to write a figure label then, we're just going to say something like this.
Oh my Lord. That was beautiful. Bull butter.
It's gotta be good.
No time.
Okay, so this plot shows a comparison of the number of protons and neutrons in all the known, it should be known N right here, known stable isotopes, okay? So, isotopes, remember, are two forms of the same element differing in the number of neutrons in the nucleus. Or, because you're changing the neutrons, you're also changing the mass, you could say isotopes are two forms of the same element differing in the atomic mass of those two forms. Okay? So what we're comparing is the number of neutrons and protons in the nucleus of all the known stable isotopes. The band of stability. Band of stability. Okay? All right. So we're going to compare, we're going to put protons down here on the, what you normally call the x-axis. This will be the proton axis here today. Number of protons. K, known, that K word right there?
Is it one word?
Known, stable, two separate words. Isotopes. Okay, so what we're going to have on this horizontal axis is the number of protons. And what we're going to put on the vertical axis is the number of neutrons.
Chill out.
So we're going to label this as 0 and 10, 20, 30, 40, 50, 60, 70, 80, and 90. And we don't have to go beyond 90. And here's why. There are no stable isotopes for any element with an atomic number greater than that of lead. There are no stable isotopes for any element with atomic numbers greater than that of lead. There are no stable isotopes known for any element that has an atomic number greater than that of lead. So what's the atomic number for lead?
90. Oh, anything up to 90.
Well, why don't you get out your periodic table and look and not just shout out an answer just because you think it might be right.
I didn't think I know. You said, you asked us a question.
Yeah, but I want you to get out your periodic table. Lead.
Can you slide up the paper up a little bit, please?
Has everybody got this down here?
Yeah.
Okay. All we got is a title and labeling the axis. It's a band of stability. Okay? All right, so what's the atomic number for lead?
90.
Lead. Atomic number for lead, 82. Okay, so I stopped at 90 because it's more than 80 and less than 90. Okay, and so our band of stability is going to stop when we get to 82. Now pay attention here. There are 1, 2, 3, 4, 5 divisions between these 80s and 90s and 10s and 20s and so forth. So this line represents not a 1 but a 2. So this is 82 right here. Okay? Just so we're clear. So there's no stable isotopes for any elements after you get past the atomic number, and the atomic number is based on protons, the atomic number for lead. So since that's where everything's going to stop, I'm going to go ahead and draw a line all the way up here to show that we're not going to go any place beyond there. That's our roadblock. All right? Just so I'm clear, I'm not going beyond there. Okay? Well, I just want to barely see it. There's a reason for that. Now,
there's a reason why you didn't want to see it?
No, you can see it, but just it's barely there. I don't want it to overwhelm what else I'm going to draw that's more important.
Okay, so that's right after 80, right?
Draw a line. Wait.
82.
Oh, 82. That's what I'm saying.
Okay, now let's label the y-axis here. We're going to have the same sort of divisions here: 0, 10, 20, and so forth.
Mr. Chen, I think you labeled 81.
Real quick.
Not 82.
There's only 5 spaces for each one.
Thank you, Mr. Chen. Oh, no.
There's one other vertical line that you want to have on here, but you don't have to have it all the way up. And I'll explain what it is later. And that's at protons equals 20. Okay? Protons equals 20. It doesn't have to go very far. Just, up 3 or 4 big lines, fat lines, whatever. Okay, now,
Might have a ruler.
so we're going to be talking a lot about the kind of things that you've learned in algebra, or if you've taken geometry, you've learned in geometry. Graphs, most of the time, in the sciences, are only in the first quadrant. Now, when you're in algebra, you're dealing with what's called a Cartesian plane, and there are 4 quadrants. But
Did you go all the way up on your line?
this one went all the way up, this one did not. This one just went up a little bit.
Dang, I can't even see that
Well,
one.
it's supposed to be kind of dim, not supposed to be really dark. Okay? It's just barely there. Okay, all right. So, if I said I want a line where x equals y, could you draw a line where x equals y? Like this? No, because x is going to be 10. Y also has to be 10 if x equals y. But it wouldn't be x equals y if it was straight across.
No, it should be straight like a steady.
Yeah, I don't know. Just give it up.
Okay, over 10, up 10. Over 10, up 10. All right, and that's the line that I want to have here. Over 10, x equals y, or protons equals neutrons. So over 10, up 10, over 10, up 10, all the way up to our intersection with the line where nothing goes beyond it anyway.
What's the last number you got there?
Up here,
Oh.
I just went almost to the top. Okay. Now then, if that's x equals y, or more correctly here, protons equals neutrons, what if I wanted a line where protons equals 1.5 times neutrons? What would that look like? Okay, for every time I go over 1 on protons, how far up do I go on neutrons? Huh? If protons equals 1.5 times, 1.5 times the protons equals neutrons, how far up do I go if I go over 1 on protons? not 2. It's not 1. It's not 1 proton equals 2 neutrons. It's 1 equals 1.5.
What was your question?
Well, let's make it easier. If I go over 10, how much do I go up? 5? That's 1.5. 1.5? 1.5. 1.5. If I go over 10, and I need to go up 15. If I go over 20, how far do I go up? 30. Okay? Because it's 1.5 times. 1.5 times 20 is 30. Okay? That's just an easier way to figure it out. But I want to go up 1 and 1 and up 1.5. Over 1, up 1.5. Over 1, up 1.5. That makes sense? But 1s are really tiny things on here. So it makes it easier if I multiply a little bit and say over 10 and up 15. Or even easier is over 20 and up 30. Over 20 up 30 be right here. Over 20 up 30 be right here. Over 20 up 30 be right here, and so forth. That's 1 proton equals 1.5 neutrons. It's that line we're looking for.
Whoa. I'm so fancy.
What?
You don't slow down. Take this in. Ruler.
It pops you upside.
So this line is protons
Hey.
equals 1.5 neutrons.
Go ahead and say it. That's mine too. Don't nobody care.
And this line is protons equals neutrons. Okay?
Oh, that was kind of like a
Yes.
At what line did you stop the protons and neutrons one?
All the way up to my boundary line here. I stopped when I got to the boundary line. Okay?
Did you hear what I said about Washington? You said he looked like Bobby Shmurda. How about he had legs? That's him there.
All right.
Can you
Yes.
slide it up a little bit? Because I can't see your ass from the back. Did you look at the top?
Greg get happy because
That says proton. What is proton?
Okay, I've got to move along because we got people leaving in 10 minutes.
Not like that.
Tell me what the words say on the line. So I need to tell.
Protons equals neutrons. Protons equals 1.5 neutrons.
And can I ask you a question?
Yes.
How come mine doesn't look like yours?
What?
How come mine doesn't look like yours?
I don't know. Now, so pay attention. We've got to cover all this before anybody leaves, and I want to get everybody out of here on time. So, stable isotopes up to element number 20, that is by atomic number. Element number 20 is calcium. Up to about calcium, proton number 20. Stable isotopes are close to equal numbers of protons and neutrons. So it will be on this protons equals neutrons line. So stable isotopes follows this line pretty much up until element number 20. Okay? Huh? Now once we get beyond 20, we're going to start to swing up. We're going to need increasing numbers of neutrons in the nucleus to keep the nucleus stable. Okay, until we reach a point where at element number 82, which is the atomic number for lead, that we need, roughly speaking, 1.5 times the number of neutrons as protons. And so we're going to intersect right here for lead. So we're going to have a smooth curve that sweeps up to that point. Okay? Now, this may be something you're not familiar with, but you know, your wrist, let me raise the camera up just a little bit here and show you something. Your wrist, compared to your pencil point, is a fulcrum. If you remember from physical science, a fulcrum is kind of like a hinge. Okay? And so if you use your wrist as a hinge and kind of practice with it a little bit, you'll probably find the right place so you can draw a nice, smooth curve so it intersects. Okay?
It's just too bendy and I
You need
want
it hard. Right, I do too.
all my friends are so confused with it.
Hmm?
Okay.
I really want to go and
My line's not looking like yours for a while. I'm just getting stressed out right now.
All right. Now, the larger the element, meaning in terms of protons, the larger the element in terms of protons, the more stable isotopes there are until you get to 92.
Make a little slow good.
Well, hold on a minute. I'm going to show you see the whole pattern. Okay? So up here, this is fatter because there are more stable isotopes up here than there are down here. Okay? So what we're going to do is fatten this out a little bit up here and work our way down until we want to like kind of a thin place down here. Okay? So we're going to kind of increase the size of this line.
Why are you scribbling over that line?
What did I just say?
What is that word that protons and what on the top? 1.5.
Neutrons. This is a graph that compares the number of protons and neutrons.
Is it me or like my graph I'm looking at like you?
exactly like I don't know what you
Went by. You said over 20 up 30, right? And like he's
Yep.
my over 20 up 30 is nothing like that. So you did that wrong.
I'm about to hit the
So this is what the band of stability looks like.
Yeah, he did that wrong.
Now, if you actually were to put on a spreadsheet the protons and neutrons in the actual known stable isotopes, this is what you get. Kind of looks like what we just drew, doesn't it? Okay.
Oh, this is what I'm supposed to draw. I like. But I like my little dark thing.
black in the field.
All right, so this is the number of protons down here. It's the number of neutrons over here. Let's look at osmium 152. Now, what does that mean? What does the 152 mean? The proton number for osmium, if you look it up on the periodic table, actually there's no elements beyond 118 anyway. No, 152 is the isotope. It's the how we identify the isotope, but it's the mass. Okay? So if the mass of this particular isotope is 152, how many neutrons are there in this isotope? Well, first you've got to figure out how many protons there are. So look on your periodic table and figure out how many protons there are in osmium, the element. How many protons? This is where everybody should be getting out their periodic table and practicing to find these things so that they'll be better equipped to do well on the test. Okay, so there are 76 protons. If you can't figure that out from the periodic table, well, you better get on the stick and figure it out because we've got a test in 2 days. Okay? It's the atomic number on the periodic table. If the atomic number is 76, well, that's the number of protons in that element. Okay? So there's 76 protons. If I have an atomic mass of 152, how many neutrons do you have? What is the mass made of? What is that mass number made of? Protons and neutrons, yes. Okay? So how many neutrons does osmium 152 have? 76, because it just used to track. Okay? Now, find osmium 152 then on this chart and figure out whether it's likely to be stable or not.
So we look at the
You find the 76 and you find the number of neutrons up here and see where it fits and see if it's stable. It's likely to be stable. Because this is an estimated curve anyway, but is it likely to be stable or not?
No.
Alright? So the argument is that it's no. Anybody disagree? Yes.
Can you explain how you can tell whether it's stable or not? Like,
If it's on this curve, it's stable. If it's not, it's not. Okay? So osmium 76. Well, this is 70, and each one of these smaller divisions is 2, and this is 6 right here. So osmium 76 is along the left edge of the ruler here. Okay? And if we're looking at 76 neutrons, then we're going to be on the bottom edge here. That's right here. And are those two things intersecting? Are those two things intersecting in the stable range? No.
oh, so stable range is with the black line.
Yeah.
Okay.
Stable range is the black line, you might say. Okay, yeah. Okay.
Hold up.
Yeah.
One more time.
Well, let's try another one. All right. How about osmium 168? Osmium 168. No, because this is the number of neutrons. Okay. What we have is protons down here, neutrons up here, and when you add protons and neutrons together, you get the mass number. And so when we say osmium 168, 168 is the mass number. To get the number of neutrons, you subtract 168 or 76 from 168. Because 76 is the number of protons in osmium. And we know that from the periodic table.
You said subtract 168 from 76 neutrons. What do you use to
Subtract the mass from the protons.
You got to find out where osmium 168 fits on this comparison plot.
You don't fit, so you got to subtract it.
The mass number is 168. The proton number for osmium on the periodic table is 76. Okay? So if the mass number is 168 and the proton number is 76, you find the neutrons by subtracting the proton number from the mass number. Because the mass number is made of protons plus neutrons. So you're saying there's 92 neutrons. Okay? So find it on your graph and see if you think it's going to be stable.
It's already outside of red line. You find the number 96? Y'all can find it. But it's already outside of red line.
Why are you trying to be funny? On the left.
So there's 92. Okay? That's still not on the line, is it? Close. And guys, I'm not going to give you one on the test that's that close and make you guess, but because we're doing it right here today, all right, I want to make sure that we have some practice with it, okay? All right, what about osmium 190? Osmium 190. Is that likely to be stable or unstable?
That's the mass number, right?
Huh? 190 is the mass number. That's correct. Is it likely to be stable or unstable?
190 from 76 compared to
You tell me. You got a calculator. Everybody's supposed to have a calculator in here.
No, that's 20 something. It's 1. No.
You say it's not stable?
No, from the crowd.
How many protons, how many neutrons in osmium 190? 114. So 114 is right there, and 76 is right here.
So yes?
I would say yeah, it's pretty much on that, right there on that line. Okay, it intersects right where the fat line is located. All right, let's try zirconium 100. Zirconium 100. Stable or unstable? Zirconium 100. Why? You got to figure that out. What's the atomic number, and therefore the number of protons for zirconium? Huh? What? Zirconium 100. What's the atomic number for zirconium? 40. Here's 40 right here. So if it's zirconium 100, how many neutrons are 60? And so the intersection is right there, to the left of the ruler and the bottom of the ruler, and that's off that band of stability.
So what if the thing went between this area? What if it went right here?
Well, that's
no,
unstable.
I'm tripping. What if it went right here? I mean, that's stable, right? Because it's in between the...
Well, but no, not in between. It's got to be on the line, but I'm not going to give you one.
On the line.
Yeah.
Okay, but you're not going to give us one in between the red and
I
black.
try not to. I gave you an example a while ago because we had this one to work with. Okay?
Gotcha.
But I won't give you one that's just really hard to figure out. Shouldn't. Okay?
Alright.
All right. How about zirconium 95? Zirconium 95. Stable or unstable?
Subtract from 91, right?
Hmm? Yeah. Now, y'all are asking me a bunch of questions that have nothing to do with the question I just asked you to help you get ready for the test. So 95 is right here. Still unstable. What? Yep. Okay, don't you think it'd be good for you to focus on what we're doing now instead of all these other things?
Yes, Mr. Ted, I agree. That's why I'm about to come up here and ask you a very educational question. Okay, can you look? So,
No, not right now. Hold on.
It's about what you just did.
I understand. Hold on.
Oh my goodness.
All right. All right, based on this band of stability, let's look at 10, 110. 10, 110. 10, Tin, the element, mass number 110. Is it going to be stable or unstable? 10, 110. Stable or unstable?
Are you still united? I had to drop the band to do it.
Yep.
I bet you do. I bet you do.
What was that? Before weight, ma'am? No. I'm sorry, what's that?
You don't think it's stable?
Yeah. No. Wait, I don't know.
Well, my line's good.
Huh?
It's like, I don't know, mine's really close. I don't know if I should.
Well, 10 has an atomic number of 50. Okay, so its protons is 50. If it's 110, what's its number of neutrons going to be?
It's 118.
Oh, sorry. I did it wrong. It's just because my line's like curved.
Yeah, that's fine. But if it's pretty close to your curve, you can assume for this exercise it's going to be pretty stable, okay?
Can I ask you a question now?